So hello, today we are going to learn about the Newton's method for optimization. So there's a function, let's say f of x, and we want to optimize that function. So how are we going to optimize that function is what Newton method for optimization does. There are other various ways to optimize a function, and one of which is gradient descent. But gradient descent is not that efficient when it comes to a larger problem. Newton's method for optimization is much more efficient and does optimization faster. So let's say the Newton's method, which was originally discovered, was to find the zeros for f of x. So f of x equal to 0. How does this do it? So for a function here, we have a graph and which is clearly 0 at this particular point. So we want to find this particular point x. Let's call it some x value, some x, right? And let's start from here. We take a random point from here. Let's call this point as x x0. This point is x0, and what we want to do is basically we are going to drop a tangent to this particular point. So we are going to drop a tangent, so the tangent intersects over here. Let's call this point as x1. Now tangent to this particular point will always get us closer to this point, which is the 0. And since this point is closer to the point which is closer to the 0 than the point which we were earlier on, we are going to consider this. We are going to draw a straight line and see where the graph intersects. This line is not straight, but consider this as a straight line. So we found a new point here. We are going to drop a tangent to this particular point. It's not a straight line, but imagine that this point is a straight line and it intersects somewhere over here. So let's call this point as a new x2. Now the x2 is much more closer than the x1 that we were on before. So we'll drop a straight line and see where it intersects. A new point here. Drop a tangent across here. We get closer and closer to this particular point which we were planning to go. So now let's go back to some maths and see that we had a function right here which was this one, and we started from this particular point over here. If I draw a straight line right down here, and we have a tangent that goes straight like this and somewhere like this, we have a triangle that forms over here. So the slope of this particular point, let's say the function is called as fx, then slope of this particular point is basically the differentiation of them, of that function, which is f dash of x right here. This point was called as x0. So I wanted to calculate or get the height for this. It would be basically putting this function in f of x0. That's what this line will give me. This height will be f of x0. Since this function is here, if I put f of x0, I will get this height right here. Now this new point here was called as x1, right? That. So what will be my slope? So slope is basically tan theta, and what tan theta is basically height divided by base, opposite by adjacent. So what I will get is f dash of x is equal to f of x0 by the adjacent, which is x0 minus x1. So now that we have this particular formula over here, which is f dash of x is equal to f of x0 by x0 minus x1. Let's generalize this formula. So what I'm going to do here is get an eraser and erase this coefficients and generalize this. And how I'm going to generalize this? I'm going to call this k. So this will be k as well, since both of them were x0, and I'm going to call this k. So what will be this? This was x0 and this was 1, so I'm going to call this k plus 1. So what we get is f dash of x equal to f of xk by xk minus xk plus 1. So if we rearrange this, we get xk minus xk plus 1 is equal to f of x by f dash of x, f of xk, sorry. So if we interchange these values like this, we get x of x k plus 1 is equal to xk minus f of xk by f dash of x. So this is basically a formula for getting a new x value that we were calculating here. We calculated this value for getting a new iterative process. If we keep on iterating, we will get closer and closer to this point. So how does this formula work for, let's say, if we start with, let's say we consider the same function and we start from here. Same function, but we start from here. Because we are starting from random point. How is it going to get me to 0? Well, if we draw a slope like this for this particular instance, it will somewhere here, this particular point, and we will drop it, and I will get this point, drop a slope like that, closer, and see, we are getting closer and closer to this point. No matter where you start from this graph, you'll get closer and closer to the point where you are looking for, which is here. And the formula for calculating the new value would be this. So this is the way where we get Newton's method, where Newton's method is used to find a zero value for a particular function equal to 0 at this particular x. At this particular x, this doesn't optimize the function, right? Optimizing is basically finding the minimum value that this particular function can produce. This particular function doesn't optimize anything. This particular method doesn't optimize anything. So what was this title all about? Newton's method for optimization. Well, let's consider a g of x as a function we want to optimize. And what is the standard way of optimizing this particular function? Is to find 0 for g of for the differentiation of g of x. We equate g of x, the differentiation of g of x, to a 0. That's the way to optimize g of x. So what if we just considered this g dash of x equal to f of x? If we have to find a 0 for g dash of x, what if we just consider f of x as g dash of x? So f of x is equal to g dash of x. Apply Newton's method on this function. This will be, we will find when this function is 0, and we will optimize g dash of x. So this is how Newton's method works.